Welcome everybody to Algebra 1, Section 6.3, Solving Systems of Equations by Elimination. So let's first talk about what elimination is. Well, the elimination method is a method for solving systems of equations by adding or subtracting the equations to eliminate a variable. So you'll notice that we specifically use the word eliminate in there. And eliminate just gives us the idea that we are getting rid of something. We don't have it anymore, which is exactly true to what the method is. So just like for graphing, when we graphed two equations, we, graphed them. And when we use the method of substitution, we substituted one equation into another. And for elimination, we will eliminate a variable. If you do not eliminate a variable through this process, you are doing something incorrectly. So we have 4 steps that we'll follow, and just like in our other methods, we won't necessarily always need all 4 steps. So the first step is to make sure that the equations are, quote, lined up. And we typically mean we want this in some sort of format to where it matches either ax plus by equals c, or alternatively by plus ax equals some c. Essentially, and we want both equations to be in the same order. So either they're both like the red or they're both like the green. And essentially, we typically just want the variables on the left and coefficients on the right, and both equations to be in the same order as far as the x's and y's go as well. Step 2 is that we add or subtract the equations to eliminate the variable with common coefficients. And I often think of this step as purely adding, and I'll explain that throughout this lesson at different points. Step 3 is to solve for the remaining variable. Step 4 is to substitute. Yes, we are doing some substitution in this method as well. Is to substitute your answer into either original equation and solve for the other variable. Step 4 is actually identical to step 4 for substitution. The only differences between these methods are the first 3 steps. It's how you get your first variable, and then how you find your second variable is the same for both substitution and elimination, both of our algebraic methods. Now, it's asking us to solve each of these systems by elimination, and I actually prefer to start with example 5. So we're going to skip examples 1 through 4 for now and come back to them in just a little bit. So for example 5, let's first make sure that both equations are, quote, lined up. By that we mean that these go x, y equals, and the regular coefficients of the regular numbers. So these are lined up. They do match each other in the format that we want them to be. And so step 1 is done. If that wasn't done, we'd have to rearrange the equations. We'll start seeing that on example 8. Anyway, now we make sure that we have matching coefficients. So that way, if we were to add these equations, would we, quote, eliminate a variable? And how we eliminate a variable is by getting 0 as the coefficient after our addition. So if we were to add 4x and negative 4x, 4 plus negative 4 is 0. And if you have 0 x's, you have no x's at all. So that successfully eliminates this variable. I like to cross that out to showcase that very visually it is eliminating. Then if we add 9y plus 7y, we get 16y. So we just do 9 plus 7, keep the y. Drop the equal sign in the same place it is. And then we do 5 plus 11 on the other side, and we get 16. Now we have this new equation. And that is step 3 for our 5 steps. Or excuse me, step 2 for our 4 steps. Apologies. Now, our step 3 is to solve for the first variable. So 16y equals 16. This is an equation that we're very capable of solving. We just have to get y by itself now, since we only have one variable left, since we eliminated x's. So we're going to divide by 16 to undo the multiplication of 16 and y, and get y equals 1. Now that we have a variable, we plug this one into either of these original equations. It doesn't matter even a little bit which one you pick. Just pick whichever one you think is going to make your life easier. Personally, I'm going to pick the top one just because it's only positive numbers. 4x plus 9 times 1 equals 5. And now as I start solving, I get 4x plus 9 equals 5. Subtract the 9 from each side, and I get 4x equals negative 4. Divide by 4, and I get x to be negative 1. And so now this will end up being my ordered pair answer as negative 1, 1. And if I had solved this via substitution, via graphing, I'd get the exact same ordered pair as my answer. Moving on to number 6 here. Number 6, we have our equations lined up. It goes x, y equal numbers. It's the order exactly we want them in, and they match. And so now we go ahead and look to add these equations. And as we add, we do 10 minus 2 for x's, and we get 8. And we do negative 3, positive 3, and that gives us 0. Our y's eliminate. We don't have any more y's, so we don't need to write plus 0y. And 18 plus 6 is 24. So now as we move on to step 3 of our 4 steps, we're going to go ahead and solve this equation for x by dividing by 8 to undo the multiplication. And you get x equals 3. So now we plug this back into either of our original equations. I'm going to pick the bottom one because even though there's a negative with the x, the numbers are far smaller, and I like that. If you pick the top one, that's fine. You should get the same answer if your math is correct. So negative 2 times 3 is negative 6. And now we do adding 6 to both sides to undo the negative 6 being added with 3y. And we get 3y equals 12. Then we divide by 3. And we get y equals 4. So now this is an ordered pair, 3, 4. Moving on to number 7, we make sure they're lined up again. X's, Y's equals numbers. They are in fact lined up. Once again, example 8 is what we'll see that they're not lined up. So we go ahead and add these equations. And as we do so, we get x plus 3x. Remember, this is secretly a 1x. So that gives us 4x. And negative 1y and a positive 1y, whether you write those ones is up to you, gives us 0y, they eliminate. And 10 plus 18 is 28. So as I divide by 4, just now solve for x. Remember, after we complete step 2 of adding these equations together, eliminating variable, we do step 3 where we solve for this variable. So now we solve for x, and we get x equals 7. And now I plug that into either of my original equations, and I'm going to plug it into the top equation because the x does not have a coefficient, and I like that. So 7 minus y equals 10. Some of us may prefer to plug it in the bottom one because there's no negatives. So I'm going to subtract the 7, even though this minus sign is here, that's with the y. The 7 is positive. And so I end up getting negative y, the negative stays with the y there, equals 3. Dividing by negative 1 gives me y equals negative 3. So I get the ordered pair 7, negative 3. Moving on to example 8, looking to see if it's lined up. It does go x, y numbers, but notice I left out equals because here the equal signs don't line up. That's because we have one y on the right of the equal sign in the top of the equation and another y on the bottom, or on the left of the equal sign in the bottom of the equation. We want them both to be on the left-hand side, the same as the x's, and so in this top equation we need to do a little bit of rearranging. Mathematically, how we do that is we do the opposite sign of whatever the y is for adding or subtracting to move it to the other side. So currently this 3y is positive, so I would need to subtract 3y from the left side and the right side. And this would get me my new equation, which I'm going to write an arrow over here. And the reason I'm going to do this arrow over here is because we need to keep our work incredibly organized for elimination to work well. Some of us may really struggle with this aspect of the organization, but I highly encourage you to work on this and be very intentional of your organization when doing this method. So, like I said, I'm going to put an arrow over here to showcase where I'm moving my work to. I'm going to have x minus 3y equals 11. We did not change anything with our bottom equation at all, so I'm just going to rewrite it but still move it over here to keep everything lined up vertically, because we said we wanted our equations lined up and matching. So just rewriting the same equation. And now we notice that these are not lined, or that these are lined up. So now we're presented with a new problem here, to where if we look to add these equations, don't actually do this yet, we get 3x minus 6y equals 27. The y's didn't eliminate here because they're both negative 3's. If one had been a positive 3, they would have eliminated. But however, we're left with this new equation. And this equation doesn't help us even a little bit. Remember how I said that if you're not eliminating a variable, then you're doing something wrong. Well, we've done something wrong because we didn't eliminate that variable. We can't solve this new equation at all. It helps us not even a little bit. So what we need to do is back up and say, okay, if this was positive or this was positive, either one, then they would have eliminated a positive 3 and a negative 3. So what we're going to do is make one of them positive. And how we do this is we multiply the entire equation, either the entire top equation or the entire bottom equation, and it doesn't matter which one. For this example, I'll showcase multiplying the entire top equation. So if I multiply the left-hand side and right-hand side of the top equation by -1, it'll do the trick. The reason I say -1, I'll showcase here, starting here with multiplying by -3. -1 times -3y is positive 3y. That gets me the exact match I want with -3y, so that these will eliminate how I need them to. And so if I multiply -1 to all three of these, x, -3y, and 11, I'll get this to work how I want it to. So I get -1 times x is -x, -1 times -3y is positive 3y, and -1 times 11 on the other side of the equal sign is -11. My bottom equation is just going to stay the same, but just like I did in the orange, I'm going to move it over so that way I keep everything, once again, lined up vertically to stay organized, so that way this method works well. And now we might be able to see that if we were to add these two equations, which we will, then we will eliminate our y's now. Once again, you could have multiplied the bottom equation by -1 as well. Some people, instead of multiplying an equation by -1, purely end up subtracting the equations instead of adding them. I'll showcase this after I complete this problem. So as I combine these, -1x and positive 2x give me positive 1x, or x. 3y and -3y give me no y, so they eliminate. And -11 and 16 give me 5. That's already solved. So now I plug this into either of my original two equations. You could choose a modified equation as well if you really wanted to of that. You cannot pick this one though because it doesn't have any x's. And so I'm just going to plug it into the top equation because it has a coefficient of x that is 1, and that makes my life easier. So I'm going to do 5 equals 3y plus 11 instead of x equals 3y plus 11. And I'm going to subtract the 11 to get my y by itself, or start to get my y by itself. And I get -5, or -6 rather, equals 3y. Now I seek to divide by 3, and I get y to equal -2. So now I have my ordered pair of 5, -2. Now I mentioned I was going to showcase what it would look like if we viewed it as subtraction rather than addition, and it's really actually the exact same thing. So what we're going to do is we're just going to take this orange step and rewrite it. So x minus 3y, let me rewrite that a bit, equals 11, and 2x minus 3y equals 16. So what you can do is just say I'm going to subtract this entire bottom equation. And here's the thing, when you subtract anything, you're secretly just adding the opposite. So I can change this to addition and change every sign in here to the opposite, including on the 16. And now as I combine, I get -x, I get no y's, and I get -5. Now that should look somewhat similar to this x equals 5, but still slightly different, because now I have both negatives. If I divide by -1 though, however, I get x equals 5 all the same. So either way works just fine. It's just a matter of how you prefer to think about it. Personally, once again, I choose the top one where I multiply everything by a -1. The main reason I do that is because it's incredibly similar to what we're going to be doing after example 11 when we jump into example 12 in just a little bit. Or excuse me, example 1 on the next page on page 12. But let's go back to example 1 in the meantime. We skipped examples 1 through 4 previously, and the reason why is because they deal with having to change signs or subtract. So on number 1 here, these equations are technically lined up even though the y's are on one side, the x's on the other. Because we have y equal x numbers. Everything's in the same spot in each equation, which is really what we're looking for, okay? Now, I still prefer to move things around to have things lined up differently because I see a lot of people making mistakes on this. I'll showcase that I'll showcase how you can do it without moving things around initially, and where people make common mistakes after I showcase how I would solve it typically by moving things around. So I'm going to rearrange by moving my 3x to the left and my x to the left. And so I'm going to subtract 3x on the top equation, which gives me -3x plus y equals 4. I always write my x before my y. Then I'm going to subtract x on both sides of my bottom equation and get -x plus y equals -2. Now, as I try and add these, I notice those won't eliminate, so I need to multiply an equation by -1. I'll just go ahead and choose this bottom equation because why not? So my top equation is going to remain exactly unchanged, as is. So -3x plus y equals 4. I forgot my equal sign. That could be important. And the bottom equation now becomes positive 1x, -1y, and a positive 2. Now as I go ahead and add these, I'll end up getting -2x. No y's left, equals 6. So I'll go ahead and divide by -2. And I'll end up getting y to equal 3, which means -3. Now I'm going to plug this one into either my original equations, or I could do the modified ones in orange or green as well. I'll just go ahead and do one of my original ones, and I'll do the bottom one because the numbers are smaller. So instead of y equals x minus 2, I'll have -3 equals x minus 2. I go ahead and just add 2 to both sides, and I end up getting -1 to equal x, which makes my ordered pair for my answer -1, -3. I did something wrong here. What did I do wrong here? Oh, I know what I did wrong here. My apologies, everybody. When I plugged this back in, and when I solved in the blue earlier, I solved for saying it was y, but that was truly x. I had made an error there, so I had 2x. And I probably confused some people there, and I apologize for that. So when I plug it back into this bottom equation, instead of y equals x minus 2, it should be y equals -3 minus 2. Now, as we complete this, we end up getting y equals -5. Now our answer is -3, -5. And that would be correct, actually, this time. Moving on to example 2 here. Here we see that everything is again lined up. We have x's, y's, equals, and our numbers. You notice though, if we were to add that, we would end up getting 2x and 3y, so neither one eliminates, so we need to eliminate or multiply at least one equation in order to make that the case. And so we can multiply either the top or the bottom equation by a -1, and that would make either the top one a -x, thus eliminating these, or the bottom one a -x, thus eliminating the x's. Doesn't matter which one we do. I'm going to go ahead and choose to multiply the bottom one here. Once again, it doesn't really matter which one you pick. The reason I'm picking the bottom one, even though it doesn't matter which one, is out of personal preference. And my personal preference here is that I want to make this negative a positive, and I want to do a positive number minus a smaller number, big minus small, I should say, 13 minus 3, to keep my answers positive. I like working with positive numbers when I can. So the top equation remains unchanged, but I keep writing it over here with this arrow to help me organize my work and to keep things vertically lined up. So now I'm going to multiply by -1 to everything in this bottom equation on each side, and I end up getting -1x plus y is equal to -3. And now I add these equations and the x's do eliminate. I end up getting 5y, and I end up getting that equal to 10. And this very conveniently works out to where I can divide each side by 5, and y equals 2. Now I need to go back and plug this into either of the original two equations. I'm going to pick this bottom one here because the numbers are much smaller to deal with. So I get x minus 2 instead of x minus y equals 3. And so all I have to do is add 2 and boom, x is already by itself and I get x equal to 5. So this creates my ordered pair of 5, 2. Moving on to number 3. Once again, we can check that it's lined up. X, y equals numbers. Perfect. Then we want to make sure, can we add to eliminate? And while these are both 3x's, they're both positive, and if they're the same sign, they will not eliminate when you add. They'll just create a bigger number. And so we need to change the sign of one of them by multiplying one or the other by a -1. I'm going to choose the top equation this time, and the reason why I picked the top equation this time, even though once again it doesn't matter, is because of these two numbers, of -10 and -9, I'd rather have this one become positive, so that way when I add them I get a positive 1y. And between 14 and 15, I would rather have 14 be the negative, so that way my bigger number is positive there. So I'm going to multiply everything in this top equation by -1, as I mentioned, and get -3x plus 10y equals -14. And then the bottom equation is going to stay the same, so I'm going to rewrite it to keep my work organized and get 3x minus 9y equals 15 like I have over to the left. Now I'm going to combine and add these equations, limiting my x's, getting 1y and equal to 1. So now this equation is already solved. Good for me. So I just plug this back into either my original two. I'll pick the bottom one. It's really kind of a toss-up because the numbers are so similar here. So I couldn't fault anyone for picking either equation. So 3x minus 9 times 1 equals 15, and that's 3x minus 9 equals 15. So I'm going to add 9 to both sides and get 3x equals 24. Divide both sides by 3 and get x equals 8. And now I'm going to end up having 8, 1 as my answer. Same idea down here on number 4. Everything's lined up. X, y equals numbers. Good for us. So now as I check, my x's don't eliminate, that'd make 2x. My y's don't eliminate, that'd make 4y. However, since they're the same number, same coefficient, just the same sign, but we need them to be different signs, I can multiply either equation by a negative. I'm going to choose this one over here on the bottom. Once again, doesn't matter. Unfortunately here, I'm having to choose between either having my x's be positive or my constants be positive, and I'm choosing my x's in this case. But once again, doesn't matter which one you pick. So the top equation I'm going to have remain the same. Bottom equation I will have multiplied by -1 and end up getting 2x minus 2y equals -18. And so I get 6x, the y's eliminate, and I end up getting -12. Divide by 6, x equals -2. Now I can plug this back into either of the original two equations. I'm going to pick the bottom one because the coefficients of x and y are smaller, but so I'm going to multiply -2 times -2 and get 4. So I have 4 plus 2y equals 18. Now as I subtract 4 from each side, I get 2y equals 14. Then if I go ahead and divide both sides by 2, y is 7. So I get my answer of -2, 7. Now that we finally finished going back to examples 1 through 4, and we did examples 5 through 8 previously, let's go to example 9 and complete examples 9 through 11 before turning to the next page. So on number 9 here, these are out of order. It goes y, x number versus x, y equals number. So in this top equation, I want to move this x to the front spot. I do that by removing the positive 2x by subtracting the 2x from each side. 2x minus itself is 0, and so I get negative 2x plus 4y equals negative 8. And my bottom equation is just going to remain the same here and get 5x minus 4y equals 20. Now everything's lined up. I have x, y equals and my numbers. So once again, we had to get things lined up this time, like we did up in example 8 previously, by adding or subtracting something to both sides of one equation. Sometimes you might have to move things around in both equations. That's very possible. Now this becomes a problem like we had on the previous page, or examples 1 through 7. So now as I look here, if I were to add these, the y's do eliminate right away, so I can go ahead and start adding rather than having to multiply an equation. So I get 3x, I get my y's to eliminate, and I get 12. I divide by 3, and x equals 4, and I solve that equation. Good for me. I plug that back into any of my equations previously, any of these 4, or really these 3, since these bottom 2 are the same. I'm going to go ahead and pick this top left one, since it's already somewhat solved for y. It's all for 4y, but it's close. And so 4y equals 2 times 4 minus 8. So it gives me, I meant to switch colors there, 4y equals 8 minus 8. And last I checked, 8 minus 8 is 0. So I get 4y equals 0. Don't panic. There's still an answer here. We divide by 4 like we would if any other number was on the right-hand side. And remember that 0 divided by any other number is 0. And so we have 4, 0 as our answer. Let's move on to number 10. 10 is lined up perfectly. We do have x, y equals numbers. However, if we were to add these equations, we get 6x and negative 8y. Neither eliminates, so we need to multiply an equation by negative 1 to change our signs. I'm going to pick the top one. It really super doesn't matter here, and you'll see why in a moment, why it extra doesn't matter compared to normal. And we get negative 3x plus 4y equals 10. And the bottom one just remains the same, 3x minus 4y equals negative 13. Now as we add these, the x's eliminate, but so do the y's. And I get nothing equals negative 3. Well, you have to have something here. And so the mathematical equivalent of nothing is 0. You have 0 x's and 0 y's, and that gives you 0 of anything. And so now we get this equation of 0 equals negative 3. And remember that whenever we have an equation that has no variables, we have to determine, is this statement true or false? And if it's true, it's infinitely many solutions, and if it's false, it's no solution. And here it is in fact false. 0 does not equal negative 3, so there is no solution because these two lines are parallel. They'll never ever intersect, touch, or cross. Finishing off this page with the notes, we have number 11 here. Number 11, things are not lined up. We have x, y equals numbers. That's the order we love. This one, it goes y equals x number. So I want to move my x from the right to the left, put that in front. Since it's a positive 2x, I will subtract 2x. 2x minus is 0. And I get negative 2x minus y equals 10. I didn't do anything with my top equation, but I do need to rewrite it to help myself stay organized. And now as I look to go ahead and try and add these equations, I note that, hey, my x's eliminate, but so do my y's. How neat. We had that happen on example 10 just a moment ago. So x eliminate, y's eliminate. We still need something on this side of the equal sign, so I'll put 0, which is the mathematical representation of nothing. So we have negative 10 plus 10, that's also 0, which we also need to write. So we have no variables, so once again we ask ourselves, is this statement true or is this statement false? Here the statement is true, so it's infinitely many solutions, or as we often abbreviate, IMS, because these two lines are actually, secretly, the same line. Now we'll move on to the next page, page number 12. So what if there are no common coefficients? So we look here at number 1, for example, before I write in what we would do. And we note that these are lined up, x, y equals numbers, and we're like, great, awesome. But if I were to add x plus 2x, I get 3x, and here I'd get negative 4y if I combine, and I don't have the ability to multiply an equation by negative 1 to solve this, because this is a 1x and a 2x, not the same coefficient, and this is a 3 and a 7, not the same coefficient. So what do? Well, what you're going to have to do is you're going to have to multiply 1 or both equations by some number to create opposite coefficients. And what I mean by opposite coefficients is the same thing we've been targeting every time, which is same number, different sign. And so instead of having to multiply just by a -1, we're going to multiply it by different numbers here. So for example, if this x was a -2x, then these would eliminate. So we ask ourselves, well, what could we multiply +1 by to make it a -2? And the answer is -2. So if I were to multiply this entire top equation by -2, we would end up getting -2x, -6y equals -12. And you may ask, well, can we do that? And the answer is yes. As long as you multiply everything in the equation, you can multiply by whatever number you wanted to. I can multiply by -592 for all I care about. It would still be true. But that wouldn't be helpful in this case. What is helpful is multiplying by -2, because now, as we keep our bottom equation the same and modify our top equation, we can see that our x's will eliminate, which is what we want. We want a variable to eliminate. And so we can proceed here by adding, and the x's eliminate. We get -13y, and we get that equal to -13. So if I divide both sides by this -13 that's multiplied with y, I get y equals 1. Now I can plug this in on both, or to one of my original equations, or this new one if I really wanted to. I'm going to pick the top one because the numbers are slightly smaller. I'm going to get x plus 3 times 1 equals 6. So that's x plus 3 equals 6. Subtracting 3 from both sides gives me x equals 3. So that's 3, 1. Now you may be wondering, Mr. Kossel, at the beginning of this equation, beginning of this problem I should say, could we have multiplied something with the y's to help us? And, well, yes, but it wouldn't be as straightforward. We'll see later, starting on example 5, where we have to do things like that. But for now, we only have to multiply one equation. But here, if we were to try and get 3, nothing times 3, or no integer times 3, non-fraction, non-decimal, would end up making it the same number as -7, or a +7 here to be the opposite coefficient. And our goal is to get the opposite coefficients. So 3 times no integer would give us +7. Not a good route to go. Same idea for -7 to 3 and 2 to 1. We'd be multiplying by half, or 3/7, and that just gets a lot more complex than we'd rather do if we can avoid it. On the number 2 here, everything's lined up. X, y equals numbers, but if we add, we get 11x, we get 4y, and neither of those are helpful. And we can't just change any signs because there aren't matching coefficients that are waiting to be opposite coefficients. So what do? Well, 2 times no integer is 9. 2 times 4.5 is 9, not helpful. And 9 times no integer is 2. 3 times no integer is 1, but 1 times an integer is 3. And we want this specifically to be a -3 here. So we're going to multiply it by -3 to this whole bottom equation. So my top equation will remain the same. The bottom equation will give me -6x minus 3y equals -5. And now we add. We get 3x, no y's, good on us to eliminate, equals 7. And I made a mistake here. When I multiplied -3 times 5 in the blue there on the far right there where I just erased, I said that was -5. That is -15. And so I actually get -3, and this will work out much more smoothly, to where I end up getting x equals -1. Now I can plug that into any of my equations, any of these equations, and I'll pick this bottom one here because the numbers are the smallest. And I get 2 times -1 instead of 2 times x, plus y equals 5. So that's -2 plus y equals 5. add 2 to both sides, and I get y equals 7. And so now I have negative 1 comma 7 as my answer. On to number 3. Everything's lined up again. X, y equals numbers. Good for us. And 3 and 5 are not opposites. 1 and 4 are not opposites, nor could they be with either of them, so we have to multiply by a different number. And 3 times no integer is 5, but negative 1 times an integer would be negative 4, which would be the opposite of positive 4. So we multiply this top equation by 4. And in doing so, we end up giving ourselves 12x minus 4y equals 56. The bottom equation just needs to remain the same by giving us 5x plus 4y equals 12. And if we combine, we end up getting 17x, no y's, and 68. Dividing by 17 yields or results in x equaling 4. Now I can plug that in, and I'll plug it into my top equation, and I'll get 3 times 4 minus y equals 14, my top original equation, I should clarify. And I get 12 minus y equals 14. Subtract 12. I get negative y equals positive 2. Divide by negative 1, and y equals negative 2. So my answer as an ordered pair is 4 comma negative 2. On to number 4 here. Lined up again, x, y equals number. Love when that happens. We do need to multiply this top equation. We could either multiply this top equation by negative 5 to make the x's eliminate, or positive 2 to make the y's eliminate. We have a choice here between the two. Now, if I'm given the choice to either multiply by negative 5 or by a positive 2, I'm going to choose the positive 2 10 times out of 10. Well, why? Well, the number's smaller and it's positive. I like both of those things. Both of those things make my life easier. And at the end of the day, regardless of which one you pick, you will eliminate a variable and be able to solve for your other variable, and your answer will be the same as anyone who does the other thing, solves for the other variable, as long as everyone does their math correctly. So whether I eliminate the x's here or the y's here has no impact on what my answer will end up being for the problem. It only impacts what it looks like and what some of the work looks like along the way, and which variable you find first. So I'm going to choose to multiply this top equation by positive 2 then, to make my life easier, and get positive 2x plus 2y equals negative 6, and 5x minus 2y equals negative 50. And if I add, I end up getting 7x, no y's, equals negative 56. If I divide by 7 on both sides, I end up getting, I meant to change colors. I end up getting negative 8. Plug that back in. I'll use my top equation because the numbers are smaller, and I like that a lot. And I get negative 8 plus y equals negative 3. Adding 8 to both sides, undo a negative 8. I get y equals 5. That results in negative 8 comma 5 is my answer. So I mentioned previously that starting on number 5, we'd have to multiply both equations, and here we'll see why. Actually, that's mistaken. We do not have to multiply both equations. I thought we would, as I was looking ahead in my notes and realized I made an error there. That won't actually come into play until we get to number 8, so my apologies on that. So numbers 5, 6, and 7 will be just like the examples 1 through 4 that we've already had. Lined up. And I need to multiply this bottom equation because the numbers are smaller here. 2 times no integer is 3, but negative 1 times an integer would be negative 3, or in this case we want it to be positive 3. So I need to multiply this bottom equation by a negative 3. And in doing so, I'll end up getting these to eliminate, which is the goal. So my top equation just remains the same. 3x minus 3y equals negative 3. My bottom equation becomes negative 6x plus 3y equals 15. I add and get negative 3x. The y's eliminate, and I get 12. Divide by negative 3, and I get x equals negative 4. I now plug that back in. I'll plug it back into my bottom equation here. And I get 2 times negative 4 minus y equals negative 5. So that's negative 8 minus y equals negative 5. Add 8. I get negative y equals 3. So I divide by negative 1, and I get y equals negative 3. So my answer is negative 4 comma negative 3. Moving on to example 6 here. We end up having everything lined up again. X, y equals numbers. And as I look, I need to multiply an equation. And if I multiply this top one by a negative 2, my x's will eliminate at negative 6, but also my y's will eliminate at negative 2 and 2. How neat. So let's go ahead and multiply this top equation by negative 2. And you may already notice something that's going to happen since we're going to be eliminating both variables, but if you don't, let's find out. So negative 6y minus 2, negative 6x minus 2y equals negative 4 is what results in the top equation. The bottom equation just remains the same, and 6x plus 2y equals 4. And as we combine and add these equations, the x's eliminate, y's eliminate, and the 4's eliminate, giving us 0 equals 0. No variables, and a statement that's true yields infinitely many solution. Or infinitely many solutions, it's plural. Number 7. So everything's lined up. X, y equals numbers. Always got to check it. Even if we are on our whatever number problem we're on right now. I believe this is 19th problem for this section. And now as I look to multiply 3 and 7, I can't multiply 3 to get to 7, but I can multiply 4 to get to 8. Specifically, I want it to be a negative 8. And so I say, oh, if I multiply by negative 2, that'll do the trick. So I do just that. And I get negative 6x minus 8y equals negative 12. And the bottom equation only needs to remain the same. And so as I add, I end up getting 1x, no y's, and positive 2. So x equals 2. Plug that back in. I'll pick my top equation. 3 times 2 plus 4y. This is a negative 2. I need to fix that because it was a negative 12 at positive 10. Glad I caught that before too much longer. And that equals 6. So that gives me negative 6 plus 4y equals negative 6. Add 6 to both sides. I don't know why in the orange I wrote that right one as a negative 6. That's a positive 6. 2 mistakes on one problem. Woohoo! 4y equals 12. Now as I divide by 4, I end up getting y to be 3. So my answer to this whole thing is negative 2 comma positive 3. On to number 8. So as I mentioned here earlier, that starting at number 8, we'd have to be multiplying both equations. Here's how we can tell. So let's first start off though by checking that everything's lined up, and it is x, y equals numbers in both equations. Now, 3 times no integer will get us 5. Same for 3 to 4. So in this case, we have to then think, okay, what could 3 and 5 both multiply up to? We want to find what's called the least common multiple, the smallest number they can multiply up to. Now, technically, we just need to find a common multiple. It doesn't have to be the smallest. So for example, 3 and 5 multiply up to 45. Now, they multiply up to smaller numbers together as well, but they multiply up to 45, and that would work. The smallest number they multiply up to is 15, and that would make our life easier than choosing 45. So don't write this down yet, but if we were to go down this route of eliminating the x's, we would need to multiply this top one by a 5, the bottom one by a 3, and one of them would need to be negative to make the signs opposite. And so let's just say arbitrarily the top one would be negative. Now, that'd be multiplying everything in the top equation by negative 5 and everything in the bottom equation by 3. Let's walk down the path of what would we need to multiply the y's by if we wanted to eliminate them. Well, 3 and 4 would have to multiply to become 12. They both would want to multiply up to 12, I should say, that'd be their least common multiple. So we need to multiply the top one by 4, the bottom one by 3, and one of them, once again, would need to be negative to change the sign and make them opposite signs. And so if I'm faced with a choice, do I want to multiply by 5 and 3 or 4 and 3? Where in either scenario, one of the numbers needs to be negative. I am personally going to choose the scenario in the red. I'll multiply by 4 and 3 because 4 is smaller than 5. That's quite literally my reasoning. Now, if you would just rather say, hey, I'm not going to bother looking at the other scenario and picking, I don't want to take the time to do that, I'm just going to pick whichever one's first or whatever, I'm just going to pick one randomly each time, whether it's X or Y's, then that's fine, you're more than welcome to. I would just encourage you to pause, take a moment, and think analytically about this problem and saying, okay, what is the easiest way for me to approach this problem? What would cause me the least amount of work as well as the smoothest path available? And it would be here in the red, the -4 and +3. And so that's what we're going to do, is I'm going to have us multiply by -4 on the top and +3 on the bottom. And once again, the negatives could be switched around. It could be the 4 that's positive and the 3 that's negative, and that would be just the same. So I'm going to multiply the top equation by -4 to every single thing, and I'm going to get -12x minus 12y equals -36. If I multiply everything in the bottom equation by 3, I end up getting 15x plus 12y equals 30. And as I add these, I get 3x, no y's, equals -6. Dividing by 3, I get x to be -2. And so it still worked out just the same once we got to this point. It's just getting there looked different on this problem. So now I plug that into any of my 4 equations here in black and green, and I'm going to pick this top one because the numbers are the smallest. And I'm going to get 3 times -2 plus 3y equals 9. And so that ends up being -6 plus 3y equals 9. And if I add 6 to both sides, I end up getting 3y equals 15. And I divide both sides by 3. I end up getting y to be 5. And then getting -2, 5. Numbers 9 through 12 will follow similar patterns of needing to multiply both equations here. So on number 9, x, y equals numbers is my organization, which is perfect, lined up well. So 5 and 7 could both multiply up to 35. So that'd be a 7 and a 5, one of them negative. And 9 and 10 can both multiply up to, well, 90 is the smallest number. So that's 10 and 9, one of them being negative again. So if I'm going to have my choice here, I'm going to pick the smaller numbers, which will be 7 on the top and 5 on the bottom, with one of them being negative. And I'm going to go ahead and make my top one negative, just because why not, I suppose. And so I end up getting -35x minus 63y equals 70. And on the bottom, I end up getting 35x plus 50y equals -5. The x's eliminate. I get -13y, and I get 65. I divide by -13, and I end up getting y to be -5. And so now as I plug this back in to any equation, I'll pick the top one, I suppose. 5x plus 9 times -5 equals -10. If you pick the bottom equation, cool. 5x minus 45 equals -10. Add 45. To both sides, and I get 5x equals 35. So now I divide both sides by 5, and x equals 7, which gives me my answer of 7, -5. On to number 10. X, y, numbers, but the equal signs. Ooh, so the y's actually aren't lined up. So I want to move this one over here, so they both go x, y equals numbers. So I accomplish that by moving the 4y of subtracting 4y. And so I end up getting 2x minus 4y equals 18. And my bottom equation can remain the same at negative 5x minus 6y equals 3. And even though things are lined up now, x, y equals numbers in both equations, I need to multiply both equations here. 2 and 5 could multiply up to 10, so that'd be a 5 and a 2. No need to change signs here since one's already negative, one's already positive. 4 and 6 can multiply up to 12. 3 and 2 would do the trick, with one of them being negative since they're both the same sign, negatives right now. So I have my choice. Do I multiply by two positives, or do I multiply by a positive and negative? Now, if I multiply by the positives, one of my numbers is bigger. So this becomes a what's your preference? Would you rather multiply by two positive numbers or a slightly smaller number that is negative? Personally, I prefer the slightly smaller number that's negative. And maybe you're different than me in that, and that's okay. So I'm going to go ahead and multiply by a negative 3 and a positive 2. Once again, which one's negative doesn't matter, but we do need one of them to be negative since they're currently the same signs on the y. And so I end up getting negative 6x plus 12y equals negative 54. And the bottom equation is negative 10x minus 12y equals 6. And so as I add, I get negative 16x, eliminate the y's, equals negative 48. So dividing both sides by negative 16, I get x to be 3. Multiply this, or so you plug this into any of my original, or any of my equations. I'm going to pick the original top equation, I suppose. Doesn't super matter. And get 2 times 3 equals 4y plus 18. So that's 6 equals 4y plus 18. Subtract 18 from both sides and get negative 12 equals 4y. Then I will divide both sides by 4 and get y to be negative 3. And so that ends up giving me 3 comma negative 3 as my answer. So number 10 was our biggest problem yet, because not only did we have to rearrange an equation, we also had to multiply both equations by a number. Number 11, we again have to rearrange because the top one goes x, y equals numbers, but on the bottom one our y is out of place. It goes x equals number y. So I need to move my minus 6y by adding 6y to both sides. And get 2x plus 4y equals 6. And the other one is 3x plus 6y equals 12. And I will again need to multiply both equations. So for the x's, I could get them both up to the number 6 by multiplying by 2 and, so let me try that again, 3 and 2, where one of them is negative. And for my y's, I could get them up to 12 by multiplying by 3 and a 2, where once again, one of them is negative. We notice these are the same. So not only does it matter which one you pick, because they're the same, but we might notice that's actually going to eliminate both of our variables here. And so we'll see that happening in a moment. So multiply the top equation by 3, bottom equation by 2. Either 3 or 2 is negative here, it doesn't matter, but one of them has to be. And so, as we do this, we end up getting in the top equation, negative 6x minus 12y equals negative 18. And the bottom equation ends up being 6x plus 12y equals 24. So as we add, x's eliminate, y's eliminate, we have 0 on that side equals 6. That is false. 0 does not equal 6, nor will it ever. So this is no solution. These lines are parallel. And on to our very last example for the day. We again need to rearrange because it goes x. X is in order, but the y in the top equation is in the right spot. The one in the bottom equation needs to move over here. We do that. We move 7y by subtracting 7y since it's currently positive. And so the bottom equation gives us negative 2x minus 7y equals 26. and the top equation can just stay the same. That's 7x plus 5y equals negative 13. And so now as we look to multiply the equations, we say 7 and 2 can multiply up to 14, so it'll be by a 2 and a 7. Neither one of them needs to be negative since they're already opposite signs. And 5 and 7 can multiply to 35, so it'd be a 7 and a 5. Once again, they can both be positive since they're already opposite signs originally. So if I'm given these choices between 2 and 7 and 5 and 7, I'm going to pick 2 and 7. So I'm going to multiply the top equation by 2, bottom equation by 7, and they both can be positive here. They technically could also both be negative here if you want to do for multiplying by your 2 and 7. That would just create a lot more sign changes that you need to do, but you'd get the same answers at the end. And so we get 14x plus 10y equals negative 26, and we have negative 14x minus 49y equals 182. And so as we combine, the x's eliminate, I get negative 39y, and I get this to be 156. So I divide by negative 39, and I get y to be 4, which means negative 4. So I plug that into any of my equations, purple or black. I'm going to plug it into my, bottom equation originally, because it's already kind of solved for x. Not exactly, but close. So I get negative 2x equals 7 times negative 4 plus 26. And so that's negative 2x equals negative 28 plus 26. And negative 28 plus 26 is negative 2. So I divide both sides by negative 2 to undo the multiplication of negative 2 on the left, and I get x equals 1. So this now results in my ordered pair of 1 comma negative 4. And with that, we wrap up Algebra 1, Section 6.3.